Hello guys, how are you doing? I'm Mohammad Sadri, and this is lesson number 13, part 1 of my ZYNQ training videos. These videos are hobby videos, so I don't guarantee the correctness of what I'm saying here. They are just to show you some concepts of designing with ZYNQ, and any case I will show what I talk about in practice on the Z board. So the title of this lesson is Reconfiguring the PL, and for part 1 we have configuring the PL with Bitstreams on SD card in a standalone mode. So as the name shows, the purpose in this video is to be able to read new beta streams from the SD card and then reprogram the PL at each moment in time with the beta streams stored on the SD card. And the whole thing we want to do in bare metal or a standalone mode. So some basic concepts about in fact PL configuration. As you know, our ZYNQ device has in fact two parts, one PL part and the PS part. This is something I have described to you in previous videos, and the PL is basically an FPGA and the PS is a complete ARM subsystem. The FPGA part of the ZYNQ device can be configured through the JTAG chain, like any other FPGA that we had in the past. So you have this test access point controller, and then this test access point controller is in the JTAG chain of your ZYNQ device, and through this chain you can program the PL. So you can transfer your beta stream through this chain to your PL and implement your desired function. This is one way to configure the PL. But in addition to this way, there are two other ways which can be used to configure the PL. Another way is through a kind of logic which is accessible most mainly by the ARM host of the PS. So you have your PS configuration access port controller, and this device, which is a part of in fact device configuration subsystem, can be accessed by your ARM host, and the beta stream can be transferred from anywhere to this device, to this controller, and then this controller can communicate with the logic which is responsible for configuring the PL to program the PL. So this is the second path through which we can configure the PL. And finally, the third path is through an IP core which is called AXI hardware ICAP, and this guy is basically providing an AXI slave interface, and through the AXI slave interface either the ARM host or any CPU or any hardware component in the system can transfer the desired beta stream in fact to the logic which is responsible for configuring the PL. So for this lesson, our focus is to use the PCAP controller, and maybe in future lessons we will focus on the ICAP. The ICAP has this advantage that can be used not only by the ARM host but also by, for example, a CPU which is already residing on the PL. So imagine that you have your ARM host and you have a microblaze running on the PL, and then the microblaze needs to reconfigure a part of the PL to implement a specialized acceleration function. Then the microblaze can use an XR hardware ICAP to reach its goal. But for now, for this video, our purpose is to use the PCAP controller, and for now, every time that we perform the configuration step, we configure the whole peer area. So in this video, I'm not talking about a partial reconfiguration in the sense that I configure only one part of the PL, but I'm talking about configuring the whole PL area. So there are numerous applications for reconfiguring the PL of the ZYNQ. Imagine that you have a kind of C program or an application which is running on your ARM host, and this application has some computational intensive parts. For those computational intensive parts, you can create hardware accelerators, and you can offload those computational tasks to your PL. So while the ARM host is running the application, at each moment in time, when it sees it requires one of those specific, in fact, computational hardware accelerators, it can read the bitstream related to that specific hardware accelerator, and it can reprogram the PL with that specific hardware accelerator, and then it can give the required, in fact, data to the hardware accelerator and receive the result. So during running the application, at each point in time, the ARM host will look what kind of hardware accelerator he needs here, and he reprograms the PL with that specific hardware accelerator. Or imagine that you are using your ZYNQ device as a kind of communication interface, or as a kind of node in a network. And then through time, through the operation of your device, at each moment in time, you are required to process a different type of data, or you are required to handle a different type of protocol, or for example, you are required to demodulate a different type of signal. For each of these cases, you need a different hardware to be implemented on the ZYNQ PL. So you will have a library of bitstreams, a library for different PL configurations, and your ARM host, depending on the task that it should do in each moment in time, it selects one of those available, in fact, bitstreams, and it reprograms the PL with that specific bitstream. So as you see, the applications of PL reconfiguration are numerous. Now, what I want to show you in this video is that suppose you have your ZYNQ device and you are in a standalone mode, so no operating system is running, and you have a set of, in fact, bitstream files or PL configurations which are stored on your SD card, and you want to be able at each moment in time to read one of these bitstreams, to copy the bitstream through the DRAM, and then to program the PL with that bitstream using the PCAP component. This is what our example is going to show. So on the SD card, we will have the FAT32 file system. So the first challenge that we will have is how In fact, I can read these bit streams from the SD card in a standalone mode. This is the first challenge we should solve. And then the next one is how I should initialize, I should configure, and I should use the PCAP controller component so that I can transfer a bit stream from the DRAM to the PL and program the PL with the new bit stream. So my example design contains 4 hardware accelerators. The first one performs just a simple addition, the second one a subtraction, the third one an increment, and the fourth one is multiplication. These are just very simple AXI slave components, and each one is representative of a PL configuration, a bit stream. Each one is a representative of a bit stream. And then the ARM host in my example is running an application that each time asks the user which one of the hardware accelerators you want to use. And the user selects a number between 1 to 4, and according to that number, the ARM host will read the bit stream from the SD card, and then it will program the PL with that specific bit stream. Now, if I was running Linux, then the process of, in fact, reconfiguring the PL using a bit stream stored on the SD card is extremely simple. In fact, the Linux operating system running on our ARM host can do the entire operation for us. All you do when you are running Linux on your ARM host is that you mount your SD card on a mount point. Then for the driver that ZYNQ has already written for device configuration subsystem, you create a node so that you can talk to that driver, which is already available and active in the Linux kernel. And then all you do is you write the bit stream that you have on the SD card to this node. Through these 3 simple commands, you will be able, in fact, to reconfigure your PL when you are running Linux on the ARM host. But in a standalone mode, the task of reading a file over from the SD card and the task of initializing the PCAP and telling the PCAP you should read the data from the DRAM and copy the data to the PL, all of these tasks should be handled with the application that you write and is going to be executed on the ARM host. So, in my example design, the first thing I do, I create my 4 hardware accelerators. And then for each of these hardware accelerators, I create a ZYNQ based hardware, and then I create the bit stream. So I will show you this step in action. Here I have the folder that contains my hardware accelerators. As I told you, for each bit stream I have just one hardware or simple block, AXI slave block, as the hardware accelerator. So I have created 4 AXI blocks, AXI slave blocks: addition, increment, multiplication, and subtraction. And they are very simple AXI slave components with one AXI slave port, and each of them it has 4 registers. And the operation of each accelerator is simple. It receives the data over its 2 first registers, and it produces the output on the last register. So if I go inside one of these guys, for example, multiplication. Then I have in the HDL folder, I have my HDL realization of this hardware accelerator. And if I look inside this design, what I see is my simple implementation that I have described to you how you can create such an AXI slave component using Vivado. So this is nothing new, you already know how to do that. The operation is actually, the flow is actually very simple. You need slight modifications in the design. As you see here, I have made a small change, and that is for the data which is being generated, this register 2, what I have is the multiplication result of the first register and the second register, and this is all I have done. So I have these 4 hardware accelerators, and with each hardware accelerator I create one complete ZYNQ project, such as this one that I'm showing here. So I have the ZYNQ PS, I have my hardware accelerator, here it is my addition, and then I have the interconnect and the logic which connects all of these guys together. Okay, and for this project that I create, I generate a Bitstream. For each of the 4 hardware accelerators I do the same. I create the project contains the ZYNQ PS and the hardware accelerator, and then I create the Bitstream. And these Bitstreams are practically those Bitstreams that we store on the SD card. And then whenever we need one of these specific acceleration tasks, we program the PL with that Bitstream. In order to convert the Bitstream into a suitable format, which then can be used for being read out of the SD card and being used to program the PL, you need a kind of conversion step. So from the .bit file generated by Vivado through this generate Bitstream here, you need to extract a kind of binary file which you can store on the SD card, and then you can use to program the PL. In order to convert the .bit file to the .bin file, you can use the bootgen utility of Xilinx. So here in my example design, I have created a simple script which performs this task for me. So here is how you issue the bootgen command in order to in fact generate the .bin file, the binary file, the equivalent binary file of your Bitstream file. The key point here is this dash split option. So what practically this function is doing is that it reads the output on line 1.beef and generates a boot.bin in split mode. And actually when I run this command, I don't use the boot.bin practically, but what I use practically is the generated .bin file. So if I look at this output underline 1.beef, I see that it looks like very similar to any other beef file that we can have for generating the boot.bin file, but as the Bitstream, I use the Bitstream for the hardware accelerator. Okay, now if we go back to our presentation, in fact this is the first step we do for creating our example design. You need to prepare the Bitstreams for each of your in fact PL configurations, and then from that Bitstream you need to generate the bin file which can be used and stored on the SD card for reconfiguring the PL. Now, as the step 2, when your hardware accelerators or PL configurations, when they are all ready, you need to develop in fact, your standalone application, which is going to be executed on your ARM host. And this standalone application is responsible for receiving the user input, which accelerator he wants to use to program the PL. And then this standalone application is responsible for reading the file from the SD card and then to transfer the data through the PCAP to the PL. So here is the application that I have created for doing the task that I want. Okay, and this application contains a set of subroutines. So one subroutine is responsible for, in fact, reading the status registers of the device configuration subsystem. Another subroutine is responsible for, in fact, unconfiguring the PL or in fact clearing up the PL from the previous configuration which is used on it, okay, to make sure the PL is in a kind of non-configured state. Then I have another subroutine. This subroutine is responsible for, in fact, testing your hardware accelerator. So when the user selects one of those hardware accelerators, we read that hardware accelerator from the SD card. We program the PL with that hardware accelerator, and then we test the hardware accelerator to show that it's working. And then I have another subroutine which is responsible for mounting the SD card, and then I have a simple function which is responsible for getting the user input, and then I have, in fact, another function which is responsible for, in fact, reading the file from the SD card. And then I have the main function which I have called program PL, and this guy is responsible for, in fact, programming the PL with the data which is being read out of the file. Okay, then I have my main routine, and the main is very simple, is very similar to the other videos that I have showed you. It begins with PS7 post config, and then I have init platform. And for init platform, the very important point is that for this example, I have disabled the caches of the ARM host, and so this reduces the performance a little bit, because when you are using the cache, then partially the data can be stored over the cache, which is much faster than the DRAM. But for now, to keep everything as simple as possible, the caches are disabled. And then through my main application, I just test the hardware accelerator, the default hardware accelerator, or the one that is already used when for the first time we boot the ZYNQ device. And then we have the mount SD card command, and then we have a loop. And inside the loop, we are getting the input, we are getting the selection of the user, which hardware accelerator he wants to program. Then we read the bitstream of that hardware accelerator, we program the PL with that bitstream, we test the hardware accelerator, and then we jump up to the beginning. Okay, so this example design and complete source code that I have here, and I have just folded them. It's available as in the shared folder, in my Dropbox shared folder. So it's a very well commented design, and if you have access to that folder, you can have a look on details of what's happening inside each function. If I want to give you, in fact, more detail of what's happening when I want to reconfigure the PL, in fact, here are the steps. Obviously, first we read the .bin file, and then I kind of unconfigure the PL, so I make sure the PL is not in configured state. Then I enable the PCAP and PCAP clock, and optionally I disable the PSPL level shifters. Then we initialize and configure the device configuration DMA engine, and then we issue the function use this DMA engine to transfer the bitstream from the DRAM, in fact, to the PL. Then we wait for the interrupt of this DMA engine and then for the down signal of the PL to arrive. And then we enable the level shifters. We apply any required reset if it is required. And then, in fact, we have our new PL running. So after this step, we can test the new PL. And this whole thing I have implemented in the example design and is available. So this step I little bit described to you. For the .bit files, you use the bootgen to create the .bin file, and actually the process is exactly the same as the process that you use to create the boot.bin file, which you put on the SD card in normal use cases, where you have the FSPL and you have a user application and you have a bitstream and you want to program and your ZYNQ device with that set. So the interesting point about this whole procedure is that whenever you turn on your ZYNQ device, the task or the set of tasks that we do here in our program, they are all being done once by the FSPL himself. In fact, the FSPL will do the very first configuration of the PL, and the FSPL for the first time reads the bitstream from the SD card and initializes the devc DMA engine and transfers that bitstream from the DRAM to the PL to configure the PL. So the whole procedure that we have in our application, in our example application, is once being executed inside FSPL. And this is why studying the FSPL source code is also a good, in fact, source of understanding how this procedure is running and how it should be done. But you may like to know, in fact, where you can find examples of how each of these two challenging tasks can be done. The first challenging task is to read the file out of FATFS file system. The second one is to initialize and use the PCAP. And for both of these, there are examples inside your, in fact, Vivado installation. So if you look at the code that I have here in my implementation, you will find in fact, a heavy correlation between this code and the example design which is available inside your Vivado installation. Obviously, I have made some changes to the example designs because that was not working, but the main idea is the same. So where are these example designs and where we can find them? So here at this address in your ZYNQ installation, ZYNQ, either on Windows or Linux, ZYNQ SDK, the version, data, embedded software, lib, and SW services, you will find, in fact, an implementation for the FAT, for reading and writing files from and to a FAT file system, in fact, a structure. Okay, so here I have this folder, ZYNQ FFS, and this is, if I go inside this ZYNQ FFS v2 on the line 2, I have examples, and then if I open this file, I have a complete example of how you can access the FAT file system of your SD card. So by studying this example, you will understand how you can read a file out of the FAT file system. So if you don't have access to my fact shared Dropbox folder, you don't have access to my source code, this is one good starting point to begin. In any case, this is a good starting point because you see how you can use this ZYNQ FFS. And as far as I know, this is an implementation which is coming from the microcontroller world, is basically developed by a Japanese guy. So, and now for, in fact, accessing and using the PCAP, where's the reference? Where are the example designs that we can study? That's in the driver that ZYNQ has developed for this device configuration interface. So its location inside your ZYNQ installation is in ZYNQ SDK 2014.4 data embedded software, and then ZYNQ processor plib, and then drivers, and then dev cfg underline the latest version that you have. And if you look inside this guy again, you have the examples folder, and inside the examples folder you have a set of examples that you can use any of them to learn, in fact, how this interface works. Okay, so these are the references, but obviously the whole thing that I have here is kind of modified version of both of these two. And then another very good point, in fact, to learn more about PL reconfiguration is chapter 6 of the ZYNQ TRM, Technical Reference Manual. So by studying the chapter 6, you will definitely gain more information about how this whole reconfiguration thing is working, and what are the reconfiguration passes, and how we configure the device in secure mode, how we do it in non-secure mode. So complete set of information is available here. So what I do, basically, I have, as I told you, these 4 accelerators, and the addition is the default one. So for the ZYNQ Vivado project of this one, I have in fact created an equivalent software development kit application, and inside that I have created my whole design, which is being executed on the ARM host. So for this set, for the FSPL, for this ELF application that I create inside my software development kit, and for the first bitstream, I create one boot.bin file, and I store that boot.bin file along with the other 4 .bin file for each of the accelerators on the SD card. So on the SD card I have 5 files, one boot.bin file which contains the FSPL and my ELF and the first default hardware accelerator, and then I have 4 .bin files, and each of them is corresponding to one of the hardware accelerators. So now if I come here into my folder, I can show you the structure of the folder. The structure of the folder contains my cores, which are the 4 hardware accelerators, the output, which contains the script which generates the .bin files from the .bit files. Then we have a simple readme, then we have the library containing routines to read the files from the SD card, and then we have the projects for each of the 4 hardware accelerators. And now I can test my implementation on the Z board and see if it's working or not, or how it's working. So here I have my SDK project, I have my application, and I have compiled the application. It's kind of up to date, and all I need to do, I come to the output folder, and then within the output folder, all I need to do is I just generate bin files, and this script for me generates all of the boot.bin and all of the bin files that I need. Okay, and all I need to do now is just copy the boot.bin and those other bin files to my SD card, and then I put the SD card inside my Z board, and then I boot the system, and then I see the result of, in fact, running the application. So here I have my SD card, and actually the content on the SD card that I use are these 5 guys. The rest of them are related to other works, and I don't use them at the moment. So we have these 5 guys, and I update these 5 guys through my newly generated files. So here we have TTY ACM0 active, and I issue just the picogram. So here is the command that I should issue for the picogram, and we have the picogram ready, and the Z board is on. So all I need to do is just press the reset button of the PS1s. Now everything will begin again from scratch. So the first messages that we have here are belonging to the first stage bootloader, and I have configured the first stage bootloader to show its debug messages. This is something I usually do. This is because something may go wrong in the FSPL and you will not understand, and your system will not boot, and you don't have any idea why the system doesn't work. So I usually keep these debug messages on. Yeah, by default they are off. So if you want to keep your debug messages on, I think you can come to this C++ build setting, and then you can come to debugging, and then inside this tab you just add -d FSPL underline debug. So as you do that, you compile FSPL, and the executable generated for the FSPL will contain the debug messages. And these debug messages, in my idea, they are very important. So FSPL has executed successfully, and then the PL is being programmed by our Bitstream, the first default hardware accelerator, which is an addition. And then we have tested the hardware accelerator. Inputs has been 10 and 11, 2 inputs, and then the output has been 21. And then now our application is waiting for our selection between 1 to 4. And each selection is standing for one of the hardware accelerators. So for now I select 2, and then I press 2, and then I press enter. And then in fact the sequence that I described to you is executed by my program. So the kind of first thing we will do, we will read the Bitstream for accelerator number 2 from the SD card, and intentionally in my program I'm showing the first and last 10 bytes of each Bitstream, just to make sure that we have read the Bitstream completely and we have read a correct file. So we have not read bullshit, we have read a correct file. And then we have the section of the code which initializes the, in fact, the configuration subsystem, shows the status of the configuration subsystem, and then it enables the PCAP clock. It disables the level shifter. This stage is, and then we look at the interrupt status register to be sure it's cleared, and then we send the Bitstream. We wait for the interrupt of the DMA controller of device configuration register to come, and then we wait for the down signal, and then we will have our PL programmed. So here we wait for the down signal, and then here we have our PL programmed, and we enable the level shifters, and then I test the hardware accelerator, and hardware accelerator number 2 was subtraction, so 7 minus 3 is 4. Okay, and then let's see what happens for 3. So hardware accelerator 3 was simple increment for the first number, for the first register. So the whole procedure as before repeats, and we have 3 plus 1, which is 4. And then finally for hardware accelerator number 4, I press 4 and then I press enter, and then we have the result 7 multiplied by 3, which is 21. So I go back to hardware accelerator number 1, and we have again 7 plus 3, which is 10. Number 1 was addition. So as you see, our system is working, our implementation is working. Our implementation is stable, so it doesn't crash, because maybe you write a program and then it reconfigures the PL for the first time and it never reconfigures the PL again. So this is why it's extremely important that before you in fact begin reconfiguring the PL, first make sure that the PL is out of its previous configuration state. Make sure there is no pending commands in the device configuration DMA, so all of the previous commands are processed. All of the in fact interrupts are serviced, so interrupt status register is clear. So when you make sure all of these are true, then you can go ahead and configure the PL for the next time. There are several important questions here. The first one is how fast we can reconfigure the PL. In fact, this speed can come very important, because you are running an application, you are the ARM host, you are running an application, and then you reach a point in your application which you need a specific hardware accelerator, and you want to in fact program your PL with that specific hardware accelerator as fast as possible. Okay, and then just some few microseconds later or few cycles later, you need another hardware accelerator. So you need to again reconfigure the PL with the new hardware accelerator. So a very important question is how fast we can do this. So definitely this example design is not showing you the best performance to program the PL. I think if we want to reach the best performance, maybe the first thing we do, we enable the caches. Okay, there are some other things that we should do as well. And then another question which rises is, what if I want to just configure one part of the PL and not the whole PL? So what if I want to have a kind of partial configuration? What will be the procedure there? So these questions are remaining. Hopefully I will answer them in future videos. So this was the first video of lesson 13. There are still remaining some parts from lesson 12 and lesson 11 and lesson 10. So there are still videos that I should create for those previous lessons. But this one I have been asked several times by different people, so I decided to create this one now. And I hope it has been useful for someone. Okay, I think that's it for now, and thanks for watching, and bye.